Okay, anyway, so let's just start a new chapter, which is the matrix representation of a quantum mechanical operator, which I already defined long time ago. Remember, this Dirac cascade could be represented by a column vector, which is the n by 1 column matrix in the n-dimensional space. The way that we do this mapping is by meshing this, say, eigenbasis or complete set of bases, say this coordinate x in and tiny little points, and these points can be infinite number of points. At each position in x space, you have a value which corresponds to that value of the wave function, okay, Schrödinger wave function. And you call this the matrix element, say alpha I, and then you assemble or you combine all these matrix elements that you meshed along the x-axis, and you call this a column matrix, which corresponds to the Dirac cascade. I won't repeat that much, but just to remind you that this is the way that we link this vector analysis and quantum mechanics. And likewise, the broad state is the Hermitian conjugate of the cascade, which is 1 by n row matrix. So this is a row matrix, a column matrix, and any quantum mechanical operator A could be represented by n by n matrix. In this chapter, we will perform some algebra and derivation to really prove and also give you some examples to be able to calculate this matrix representation of a quantum mechanics. For example, the angular momentum operator. Suppose L equals to 1, and we have, say, 3, say, quantum numbers, m equals to 1, 0, or minus 1. So then you could expand all this eigenstates of the angular momentum operator, say LZ, in terms of the 3 by 3 matrix. Okay, so this is what we will do. We will also try to figure out the eigenvalues of this matrix as a quantum mechanical operator, and how to diagonalize this matrix operator, find the eigenvectors, and so on. So let's just, again, follow this line of thinking. So let's just talk about this angular momentum operator. LZ is this. So later we will use a matrix for a particular given angular momentum quantum number L, and to expand all this, say, eigenstates of L squared and LZ in terms of a matrix. Another example is the harmonic oscillator problem. Remember, the nth eigenstates is given by this operation, where we take the elevator up to nth floor. This operator that plays the role of the elevator is a dagger. So we start from, say, the ground floor, take the elevator up to nth floor. We could also use this matrix to represent this eigenstates of a harmonic oscillator problem, and also the A operator and A dagger operator, okay, which takes us to 1 floor above or 1 floor down. So remember, in the harmonic oscillator problem, we have this eigenvalue equation. We have this raising operator A dagger, lowering operator A, and those eigenstates are orthogonal and normalized. And we also have this completeness relation, which says that if you sum of all this projection operator, remember this is our projection operator, P, after summing over all these eigenstates, you get unit matrix. Okay, so let's just look at this matrix representation of the harmonic oscillator problem first, and then we'll go back to this angular momentum operator later. To construct this matrix element of this harmonic oscillator operator, so let's try to construct this Hamiltonian matrix. Okay, so H, as I mentioned, when H acts on this eigenstate n, this gives you this eigenvalue h bar omega times n plus 1/2 times eigenstate itself. Okay, so what is the matrix that corresponds to that kind of a eigenvalue equation? You could very easily see this correspondence. Suppose I consider this H as a matrix. I sandwich this matrix by this Dirac-Broglie M on the left and the Dirac-Cast on the right. This is what I call this matrix element. Of course, we need to prove this, but we'll do that later. So this is the matrix element of H, which I call this HMN. Suppose this M and M are eigenstates of harmonic oscillator, and it is easy because you can simply just use this eigenvalue relation right here. So you could simply just plug in here. H, the Hamiltonian operator, when it acts on this eigenstate, eigencat state n, it gives you the eigenvalue, which is h bar omega m plus 1/2 times the eigenstate itself. But this h bar omega and also this n and 1/2 are just numbers. So you could just move this number around. Okay, so this gives you the number, the eigenvalue times this matrix element, which is the inner product or dot product between the Dirac-Broglie and the Cast state. Remember, this state M as a Dirac-Broglie state is what? Is a column matrix, right? And Dirac-Broglie state is the row matrix. Dirac-Cast state is a column matrix. And so these Broglie and Cast states are the eigenstates of harmonic oscillator. They should follow this orthogonal and normalization condition right here. So without even computing this matrix product, you immediately see that this is nothing but the Kronecker delta function, delta m, which is 1 if n is the same as n, and 0 if m is not the same as n. As a result, you immediately see this matrix element, which is a number times delta function. So now you are able to really construct the matrix representation of a harmonic oscillator. Hamiltonian, which is this big matrix. The ground state corresponds to n equals 0 state, where the matrix element is simply just your eigenvalue, eigenenergy, 1/2 h bar omega. The first excited state is what? 3/2 h bar omega. This is the ground state, and this is first excited state, and so on and so forth. So only the diagonal direction shows finite value, where these values are nothing but the eigenenergies. And all the other matrix elements are 0 because of orthogonal and normalization condition. M plus 1/2. Okay, so this is again, the trivial example of the matrix representation of a harmonic oscillator, which is the diagonal matrix. Only the diagonal elements are finite, and all the off-diagonal elements are 0. Okay, so this is very straightforward. And you could do the same thing to construct this A and A dagger, because now to construct, for example, this A dagger, so now the matrix elements are non-trivial, because if you applied a dagger to this state n, you get n plus 1 state. Okay, it's not the same state. Okay, As a result, you get off-diagonal matrix elements non-zero. You could play the same game. 0, 1, 0, 0, square root of 2, 0, 0, 0, 0, 0, and square root of 3, 0, 0, 0, and so on. Remember, the finite matrix element appeared only along this direction marked by yellow, which is just a shift of this diagonal elements by, say, one matrix element. And remember this, so we will see that in just a moment. Okay, so this represents the ground state, first excited state, second excited state, and so on and so forth. You could very easily see this kind of matrix elements from this relation right there. Okay, so let me just mention this, say, the matrix representation of the eigenstate. In the harmonic oscillator problem, so we could very easily construct this, say, state n as a Dirac cat state, which is the state is a column matrix, which is normalized to 1 only in this nth component. All the other matrix elements are 0. Likewise, if you simply just take a Hermitian conjugate of this cat state, you get this broad state, which is a row matrix. Again, so this will be the same thing. The unit 1 appears only in nth component of this row matrix. So then you could very easily use this matrix representation of harmonic oscillator problem to actually recover all this relation right here. So as we will see later part of the lecture, that you could very easily see this correspondence. Say, if you act this Hamiltonian matrix on this state n, eigenstate n, you get your eigenvalue times the same thing. Likewise, you could reformulate this kind of a racing operator A dagger acting down the state n gives you the state n plus 1 times this prefactor. This is given by, again, this A dagger matrix acting on this matrix, which gives you square root n plus 1 times n plus 1 state, where this 1 right here on the left of the equation appears at the nth component of this eigenstate n, but on the right hand side it appears as n plus 1's matrix element of this state n plus 1. You can check this by simply just using this big matrix, and as I mentioned, you could simply just multiply this by any eigenstate of a harmonic oscillator, say 0, 1, 0, say this is nth, and you check, what is the results after you make such a matrix product. Okay, so the prefactor will be this matrix element, square root of 1 plus n times n plus 1 state. Well, you could very easily check this. There's a final remark. So we will actually repeat that or come back to this remark later. So this, just to remind you that this complete set of bases does not necessarily corresponds to the eigenbasis of this operator. For example, this is precisely the point. This n state n is the eigenstate of the harmonic oscillator, the Hamiltonian H. However, this is not the eigenstate of a dagger, because when I apply this relation of this racing operator A dagger, on the right-hand side of the equation, this eigenstate is changed from n to n plus 1. So this is not the eigenvalue equation. This is simply just a relation between, say, n and n plus 1 states by a dagger operator. As a result, the state n is not the eigenbasis of a dagger operator. We will come back to this in just a moment. And you can very clearly see this, the statement over there, that if the state n, the eigenstate or eigenbasis of Hamiltonian, of harmonic oscillator, is also an eigenstate of a dagger, then the non-zero matrix element will appear only along the diagonal direction. Okay? As shown here, we'll see in just a moment that when you have a matrix represents the quantum mechanical operator, only the finite matrix elements appeared along the diagonal directions. In other words, if the eigenstates form the matrix which diagonalizes Hamiltonian, then those eigenstates can be formed as eigenbasis, okay, of the Hamiltonian matrix. But if the matrix is non-diagonal, which means that you have the finite off-diagonal elements, then the states that you expand this operator around is not eigenbasis. It is a complete set of a basis, but it's not the eigenbasis of this operator. Okay, so the state n is the eigenbasis of Hamiltonian, but it's not the eigenbasis of a dagger. It is just a complete set of a basis that you could expand this a dagger in terms of matrix form. 我用中文再说一次好了，就是这边我们特别强调，你可以用来表示一个量子力学的这个算符，用 matrix 矩阵来表示的这样子的一个基底空间呢，它可以是这个 operator 的本真空间eigenbasis 本真基底，或者是不是它的本真基底。用这个例子来看，如果是简谐正子的 Hamiltonian matrix 呢，它的 matrix element 只有在对角线的方向是有限是不为零的，其他的都是为零的。那这样就表示这个 eigenbasis 这个 basis 用来展开这个 Hamiltonian matrix， 它是这个 operator 的本真的基底空间eigenbasis。那如果这个 operator 被你这个基底展开之后，它并不是只有这个对角线才不为零，而且非对角线的方向是有 matrix element 不为零的 matrix element， 那它就不是它的本真基底，但是它仍然是一个基底。所以这个基底它可以是本真基底，也可以不是本真基底，但是不管是不是本真基底，它都是一个基底。这样明白吗？ So you could expand your operator in any basis, but this basis may or may not be the eigenbasis of that operator. If this basis is the eigenbasis, then your operator in the matrix form should be a diagonalized matrix. If not, then your matrix is non-diagonalized, which appears a finite off-diagonal matrix elements. This is an important point. Okay, so let's take a short break. When we come back, we'll continue analyzing this matrix representation of a quantum mechanical operator.
不好意思，可不可以请老师再解释一下 A dagger 那边的矩阵是怎么来的？
你就用这个式子可以得来啊。如果你的 n， 你的定义的 n 就是这个 column matrix 的话，那 n 这个 state 代表的是第 n 个 matrix element 是1，其他都是0。你就把这个 matrix A dagger 作用到任何一个 n， 你就会得到这个式子。你把 n 当作是这个 n 加1，就是1出现在第 n 加1个 matrix element 那个地方的 column matrix。因此，你这个矩阵作用到这个 state n， 就会得到根号 n 加1乘上 n 加1这个 state。明白吗？
好，谢谢。
OK， 好。I think this is one of the key calculations in quantum mechanics, you must learn this matrix multiplications as a quantum mechanical operation. There is a reason for us to learn this matrix representation of a quantum mechanical operator, and this is the reason. If we adopt this matrix representation of an operator, then many quantum mechanical operations could be very conveniently performed. Let's derive this kind of a correspondence more rigorously between this quantum mechanical operation and the matrix product. Suppose this capital F and capital G are quantum mechanical operators. As we already defined, we could construct a matrix based on this complete set of bases M and N, and this is defined as our matrix element. This Fmn is defined by this kind of a matrix product between, say, among this row matrix and n by n matrix and the column matrix. Remember, this is given by what? This is a row matrix, n by n matrix, a column matrix. So it's 1 by n times n by n times n by 1 is a 1 by 1, which is a number, which is what we defined as matrix elements. And you can construct this matrix F based on the matrix element. Likewise, capital G is another quantum mechanical operator which can be represented by a matrix of n by n size. You could operate this, take this operation by applying this capital G onto any arbitrary Dirac state J. You can expand this in terms of this complete set of bases, state n, and remember this is a unit operator, which is this thing. To expand this in terms of a complete set of bases n can actually lead us to this matrix element representation of this operation, where you could simply just define this G sandwich in between this broad state N and cat state J as this matrix element. Okay, times this cat state N and you sum over N. We should prove that this kind of matrix product or matrix representation of an operator satisfy what we expect for a real matrix product multiplications, and which says that if I have two matrices F and G and I take the matrix product between them, and after that take the matrix element Ij, and what I get is this kind of a summation. In doing so, I do not assume that F and G are any operators. This F and G are simply just a matrix. It doesn't need to be an operator. But we will see in just a moment that if we defined the operator in quantum mechanics in this matrix form, and automatically it is satisfied, okay, which means that we are okay, or it is justified for us to really use this matrix representation to represent this quantum mechanical operator, because they satisfy this matrix multiplication in mathematics, which in general should hold without interpretation of the matrix being the quantum mechanical operator. So let us just try to make such link, and suppose this is a matrix multiplication F times G. I sandwich this by this Dirac-Broad and cat state. I could just use this unit matrix 1, which I could insert any place I like. I decided that I could insert it in the middle between F and G. But if I do so, I get very easy interpretation, namely the matrix element of F and G. As a result, this is simply sum over n, Fi and G and J, which is exactly the same form because n is just a dummy variable, I can rename this, relabel this. I can call n k, fik, and g k j. Check. Okay, so this kind of quantum mechanical operation satisfy what to expect for matrix multiplication for general matrix. Indeed, we are okay to actually use this matrix representation. So from now on, we could safely just adapt this matrix representation for any quantum mechanical operator and also any quantum states. So let me just come back to this basis, eigenbasis or non-eigen basis, this remark that I just made. So if n, the cat state n, are the eigenstates or eigencats of an operator A, then this operator A can be written in terms of a diagonalized form. The reason is really simple. As I mentioned, because we have this eigenvalue equation, and suppose I define my eigenstate or eigencat as a unit column matrix where this matrix element, only non-zero matrix element 1, appears at nth component. And then you can very easily see that if I construct this matrix elements of the operator A, only this eigenvalues, which are non-zero, will appear along the diagonal. Off diagonal matrix elements are 0, and this is really easy to see. If I have this A1, A2 up to an as my matrix for 8, I simply just do this algebra by applying this A operator onto the state n. What I get is this. Remember, this column matrix state n shows non-zero matrix element only at nth component, in nth component. All the other components are 0. As a result, you get an times the same thing, which is an n. Sounds trivial. So it's a one-line proof. Suppose this n is the eigencast of an operator A, then this operator should be a diagonalized matrix. Okay, it is a diagonalized, already diagonalized. But if I expand this A operator in terms of other bases, then operator A may not be diagonalized in general. But this is just a trivial case where you indeed expand this operator A in terms of the eigenstate of that operator. Of course, this matrix is the diagonalized matrix. So let's try to diagonalize arbitrary quantum mechanical operator in the matrix form. Diagonalizing an operator matrix is very important in quantum mechanics because, as I mentioned, we need desperately to know the eigenvalues of any quantum mechanical operator and eigenstates. So the way that we know this eigenvalues, eigenstates, of course, in the matrix form, is to diagonalize this matrix. As I mentioned, suppose I expand this A dagger operator in the harmonic oscillator problem, and you will get non-zero matrix element along the off diagonal. As a result, if you would like to know this eigenvalue of this A dagger operator, then you need to diagonalize this. So we need to diagonalize any arbitrary quantum mechanical operator in the matrix form in order to know this eigenstates and eigenvalues. How to diagonalize the general matrix? Well, this is trivial because you already learned that. Mathematical physics, okay, applied math, and so on. Okay, so you know how to diagonalize general matrix. We won't repeat that much, but I'll emphasize the key points. As I mentioned, this is non-zero in general. However, if I know this eigenstate of an operator A, and I can expand this in terms of this eigenbasis, and that eigenbasis A is diagonalized. In this basis, it's diagonalized. But if I expand this A operator in different other bases, this may not be diagonalized. Of course, it should not be diagonalized if this un or un are not the same as this alpha n. So now suppose we expand this operator in terms of this non-diagonal basis, namely the un basis. Suppose, and we should know the eigenstate of this operator A, namely we should know this alpha. Okay, so what do we do? Of course, we need to diagonalize this general matrix. The way that we do this is to first you diagonalize this big matrix and find the eigenvalues, you find the eigenvectors. Suppose you know the eigenvectors. First, diagonalize this A. You get eigenvalues, which is AI, and then you could construct this eigenvector. So let me just write down this, the big matrix. Okay, suppose we follow the knowledge that you already learned to diagonalize the big matrix Aij, non-zero in general. We find eigenvalues, and which I denoted by AI, A1 up to AN. And then you could construct the eigenvector based on this eigenvalue. Each eigenvalue should correspond to one eigenvector, which I call this Dirac-Caste A1 up to Dirac-Caste AN. So then you could construct the big matrix, which I call this U. And this big matrix U is made of all this eigenstate or eigencat. You could actually combine all this column matrix as these eigenvectors corresponding to a particular eigenvalue A1 up to AN. You can simply just merge all these eigenvectors and construct the big matrix based on these eigenvectors. You have n components of each eigenvector, and you have n eigenvectors. Combining everything, you get n by n matrix. Okay, so this big matrix can actually diagonalize your general matrix. We will just see in just a moment. So if you apply this so-called unitary transformations, that you make a product of the three matrices. So from the left to the right is U dagger and U and A and U. So if you make this matrix products among the three matrices like this, you immediately see that the final result is nothing but the diagonalized matrix that you're looking for. And then you could, based on this, you could actually represent all the other operators based on the eigenstates or eigenbases of this operator A. So let's take a short break. When we come back, I'll provide you with more details along this kind of calculation. In some mathematical textbooks, this matrix U is called this eigenvector matrix. It's a matrix made of eigenvectors. And this eigenvector matrix can be used to diagonalize your matrix. So let's just derive this statement that I just made. Suppose I could find this eigenvalues, eigenvectors of a matrix A. I call this eigenvalues A1 up to AN. I call this eigenvectors the caste A1 up to caste AN. I simply just combine all these column matrices together. I can define this unitary matrix U, which satisfies this unitarity. If you make a dagger of this, multiplied by U, and you get a unit matrix. And this is obvious because of this orthogonal normalization of this eigenvectors an. And suppose I take the matrix element of this U matrix, I take this in components of the U matrix and define this as nth eigenvector, i's component of the nth eigenvector. And this eigenvalue equation could be formulated in terms of the matrix product. Suppose this is the matrix A multiplied by this eigencat an cat state, which gives us this eigenvalue an times this eigencat. So in terms of matrix element, this is nothing but the summation over J. You take the matrix element Aij times this matrix element n's J's component of the nth eigenvector Anj, which gives you this eigenvalue times this, again, the i's component of the nth eigenvector. So, and we plug in this ansatz in here, we'll see that for a general matrix A, by doing so, we can construct the diagonalized matrix. We can diagonalize this matrix. So the way that we show this is simply just take the matrix element of this matrix product, U diagonal AU. I take the Mn component of this matrix, and I simply just expand all this matrix element in this product by summing over I and j of these three matrix elements. Remember, U dagger mi component is actually U star im. So you need to switch this matrix element and take this complex conjugation. And then you could focus on this two, and you sum over j. If you simply just expand this Ujn component as this j's component of the nth eigenvectors I define over there, then you immediately see that this summation over j, this aij times this j's component of the nth eigenvector is nothing but this eigenvalue equation over here. All right, so you apply this eigenvalue equation and you get eigenvalue times this i's component of the nth eigenvector ani, and since an is simply just the eigenvalue, it's a number, you could just pull this back. You do this remaining summation over I, and this is nothing but the square of your matrix element, which is what? This is simply just the inner product between the state m and n. And we know very well that this is nothing but delta mn. It vanishes if m is not the same as n. It is 1 if m is equal to n. This is nothing but an n, which is the square of this thing. This is nothing but diagonalized matrix, because only the diagonal direction gives you the finite non-zero matrix elements. All the off-diagonal elements are 0, and so we're done. So this is the way to do. Guys, remember, when you diagonalize the matrix, this unitary matrix U could be constructed in this way. Of course, this is not the order that we diagonalize matrix. What we really want to do to diagonalize the matrix is to do this determinant. Suppose this is a big matrix. We would like to solve this eigenvalue equation, namely the operator in the matrix form acting on this eigencat alpha is actually the same. You could get this eigenvalue equation. Suppose for general eigenvectors, which is denoted by this alpha column matrix, alpha 1 to alpha n as matrix elements, and then you simply just move this to the left from the right. This is the matrix that you already move that you move your right-hand side of the equation to the left-hand side, and now the equation, eigenvalue equation, becomes this matrix equation right here. Along the diagonal elements, you have this minus a, where a is your, or ai is your eigenvalue, and all the remaining matrix elements are the same. So you need to solve this matrix equation, and the solution for this ai is when you have this, the solution for determinant. In other words, as you already learned in your applied math, you need to take the determinant of this matrix. This is the polynomial equation for ai, and then you solve for ai, because you know all the matrix elements, capital Aij. This is the way to do. This is the polynomial in A, which is 0, and then you solve for A. So once you solve these eigenvalues, ai, you could continue to look for this eigencat. The way that you find this eigencat is, again, by plugging your eigenvalue. Multiply this, say, the matrix A by your unknown eigencat, which gives you the eigenvalue times this eigencat. Of course, you need to assume all this matrix element of your eigencat to be from A1 to up to AN. So then you need to solve all this linear equation. So n couples linear equation. So you could simply just multiply this with that. You get the first equation, which is given by ai times a1, and so on and so forth. So you get n unknown variables, that you get n equations. And therefore, you could look for the solution for those matrix elements, a1 up to an. And then you need to normalize this. And this is the way that you find this eigenvector. We will perform such a simple exercise in just a moment. Okay, so let's take a short break. So I believe you have done this already. Let's look at a very simple example of this eigenvalue, eigenvector problem. Our textbooks listed a very simple exercise that we could diagonalize the matrix M3. We'll see in just a moment that the M3 is nothing but this one of the angular momentum operator when L equals to 1. So it is expanded in terms of the 3 by 3 matrix with the matrix element minus I and I appearing here and there, and all the other elements are 0. It's very easy to find this eigenvalue. You simply just make this equations by demanding that the determinant of this matrix M3 minus lambda times this unit matrix I vanishes, whereas lambda represents the eigenvalue. And there are 3 roots of this cubic equation. This is lambda to the power of 3 in the polynomial, and in general you have 3 eigenvalues which corresponds to lambda 1 being 1, and lambda 2 being 0, and lambda 3 being minus 1. So you could plug in this 3 eigenvalues individually, separately, and look for the eigenvectors that satisfy the eigenvalue equation. And you normalize these eigenvectors, and these eigenvectors are this one, lambda 1 cat state, lambda 2 cat state, and lambda 3 cat state. I skip the details. I think you could do that. This is just simple algebra. So now here comes the important part. So you now know the eigenvalues, eigenvectors. You can actually compose this the big matrix U, which I just mentioned. In this very simple example, you simply just combine these 3 column matrices together, and you define this as a 3 by 3 matrix, which I call this unitary matrix U. And now you just make a matrix product multiplication among U dagger M3 and U, and you get exactly the eigenvalue of Z component angular momentum when L equals 1, which is 1, 0, and minus 1, appearing along the diagonal directions. So this is just a simple exercise. In general, you could follow the same procedure to find all those eigenvalues, eigenvectors, and unitary matrix that diagonalize the operators in the matrix form. So now let's look at this matrix representation of the angular momentum operator.